Hi everyone, today we're going to cover compounds and bonds. So we're going to go over the basic of ionic bonding and covalent bonding. So I'm just going to shrink myself so you don't have to see me. Okay, so the first thing we're going to talk about is the octet rule. And that is the idea that a complete outer shell, so those valence electrons, when you have a full shell, there is this associated stability with it. And we see this with the noble gases. This is why the noble gases don't interact with anything. So they're just happy as they are because they're stable. Now, the idea of the octet is that there are 8 electrons that can be filled in that outer shell. The only exception is helium, which is complete with a duet, just 2 valence electrons. So our whole goal in bonding is to get a complete outer shell filled with 8. Or 2 if we're considered hydrogen. So we can get to this stability by 2 ways. We can either transfer electrons and completely give one away or take one on, gain or lose, to become complete. And in that way we're an ionic bond because we're forming ions. Or we can share electrons between elements. And we see this with nonmetals with covalent bonding. So atoms are going to do this to become more stable overall. And we're either going to gain, lose, or share valence electrons. And remember, it's those outermost valence electrons that are the ones that determine the chemical properties, the physical properties, and also the reactions that are going to happen. And we're going to do this by forming either an ionic bond or a covalent bond. This is how we're going to reach our stability. Now we're going to transfer those electrons or gain or lose if we're forming an ionic bond between a metal and a nonmetal, or we're going to share pairs of electrons, and that is going to form a covalent bond only between nonmetals. So let's talk just quickly about covalent compounds. So covalent compounds are formed when nonmetals share valence electrons. Those form covalent bonds. We can have covalent bonds that are single bonds, which is 1 paired share of electrons, double bonds, which are 2 paired shares of electrons, or triple bonds, in which atoms share 3 pairs of electrons. And here are just some examples of these covalent bonds. We have water, carbon dioxide, and glucose. These are all shared electrons between nonmetals. So again, covalent bonding only occurs with our elements that are to the right of the step, and those are going to be our nonmetals that are in yellow. And the only one that's to the left of the step is hydrogen. Ionic compounds, on the other hand, these are formed when a metal atom transfers electrons to a nonmetal atom. Okay, this is an ionic bond. So both of our atoms form ions. In this case, all metals are going to become positive ions because they are going to give away or lose an electron. Because they're losing an electron, they're going to have more protons, so more positives in their nucleus, than they have electrons floating around. So they'll have a plus charge, either a +1 or a +2 or a +3, and this all depends on the group number. So they're all going to give away their electrons. Now nonmetals, on the other hand, these are going to gain electrons or take them on, and because they're gaining in electrons, they are gaining in a negative number. So they will have more electrons than they have protons. So in this case, if we look at these are going to become what we call anions or negative ions. And depending on the group number, they will either have a -1, -2, or a -3 charge. And these are just examples of what we call ionic compounds. The first one, table salt or sodium chloride. Then we have baking soda and milk of magnesia. And in these cases, the last 2 are what we call polyatomic ions. Okay, so if we're looking at the anion complex, it is consistent of multiple atoms, so it is considered polyatomic, but it has 1 charge overall. and we will discuss these. These both have a -1 charge. We'll get into that afterwards. So the first thing we're going to do is look at ions and ion formation. It would be really handy if you had a periodic table next to you so you can reference it as we go on. So we're focusing solely on metals first. So all of our metal ions are going to form cations, or these positive ions, because they're going to give away electrons. So metals form positive ions called cations, and they lose valence electrons. So they're transferring them. They're giving them away. Now group 1 form a +1 charge. Group 2 form a +2 charge, and group 3 form a +3 charge. And what I'm going to do is I will have little videos online on Moodle explaining why in more detail about why they're giving them away, because they want to get that next complete outer shell. So anything in group 1, it only has 1 valence electron. Now it's easier for it to give up 1 and have the complete 8 underneath that next shell down than it is for that to gain 7 more electrons. So it's easier to give away 1 than gain 7, so they become a +1. With group 2, they have 2 valence electrons. It is easier to give away 2 than it is to collect 6. So again, these are going to give away 2 and become a +2. And the same goes with group 3. With group 3, with atoms like aluminum, it's easier for it to give away 3 electrons than it is to get 5. So here is our sodium atom. Now sodium overall has 11 protons and 11 electrons. Sodium is in group 1. It has 1 valence electron. There it is. So it's easier for that to give away its 1 electron than it is, again, to gain 7. So when it gives away 1, it still has its complete outer shell underneath. And what happens now is it has 11 protons, but now it only has 10 electrons. So if we're looking at the total charge, 11 positive, 10 negative, it leaves us with a +1 charge. Okay, so we're just looking here, 11 protons, 11 electrons. In the neutral atom, we have a 0 charge. In the ion form, we have a +1 charge. If we're looking at atoms in group 2, an example is magnesium. Magnesium achieves an octet by losing 2 of those valence electrons, the only 2 it has, because it's easier to lose 2 than it is to gain 6. Because of that, we go from 12, we still have our 12 protons, but now we have 10 electrons. And again, if we look at the charge difference between 12 and 10, we have a +2 charge. So I'm going to ask you to think about aluminum. Aluminum itself is Al. Aluminum is in group 3 of the periodic table. So what is the number of valence electrons in aluminum? That one would be 3. What does aluminum require to achieve an octet? Is it going to gain or lose those 3 electrons? In this case, it's going to lose those 3 electrons. So it's going to give them away. Otherwise, it would have to gain a total of 5. What is the charge of the aluminum ion afterwards? Because it gave away 3, it is now going to be a +3 charge. And if we asked about the symbol, what you would do is write Al3+. So those are the answers for you. So now let's focus on nonmetals. Nonmetals, like I said earlier, are going to form what we call anions. So these are negative ions. They're known as anions, and they gain in valence electrons. So anything in group 7, remember our whole goal is to get to 8. It has to become complete with 8. So anything in group 7 is going to gain 1. And because we're gaining 1 electron, we become a -1. Anything in group 6 needs to gain 2, so it becomes a -2. And anything in group 5 becomes a -3. So let's look at chloride. This is in group 7. Because it is in group 7, it has 7 valence electrons. Here they are, if we're looking at the electron dot formation. Now, it is easier for chlorine itself to gain 1 electron than it is to get rid of all those 7 around it. So because it's easier to gain 1, originally if we're looking at the atomic number for chlorine, it's 17. So it has 17 protons, it would have 17 electrons. If we gain 1 electron in, now what happens, we're going to fill in that electron right here. We now have 17 protons, but 18 electrons. We now have a -1 charge. So there that is, if you're doing the math out, -1. We've expanded our electrons. So we have to think and know, we know about our valence electrons, how they're related to the group number. The group number is equal to the number of valence electrons. Now let's look at the charge. Now, in our positive ions or our metals, for our metals, the group number equals the charge number because they're positive. Group 1 is +1, group 2 is +2, and group 3 is +3. For our negative ions or our anions, you are going to subtract 8 or 18 from the group number. So if you're using like the 6A group number, we're going to subtract 8. If you use 16, just subtract 18, okay? But anything in group 6, we're going to go 6 minus 8 gives us a -2, okay? If we had a 5 here, 5 minus 8 would give us a -3. Or group 7, 7 minus 8 gives us a -1. You might be asking why we're not talking about group 4. Well, group 4, we really don't see a lot in ionic bonding. Group 4, you could go either way. There's no real gain or loss. Group 4 tends to share their electrons. And group 4 with carbon in it, we're going to see mainly come back with covalent bonding. So here are those typical charges for anything in group 1. Lithium, sodium, potassium all have a +1. If we're talking about our group 2 cations, including magnesium, calcium, barium, they're all +2. Aluminum is in group 3, so it would be a +3. For our group 5 anions, we're talking about our nitrogen, our phosphorus, and our oxygen. Okay, so these are going to become ides when we'll start talking about naming them, but we have our -3 charge. For group 6, we have oxygen and sulfur. Those are our -2 charges. For group 7, we have fluorine, chlorine, bromine, and iodine, which will all be -1. So remember, metals lose electrons to get to their shell below them, the complete outer shell below them. So we're going to a noble gas configuration here. And because we're losing electrons, we're becoming positive. Now, nonmetals are going to gain electrons to become their next complete octet, or what is considered the noble gas next to it. Okay? And we're gaining, so we're becoming negative. Just to give you an idea again, to show you these charges. So it is important to know these charges for an exam and for a quiz. That group 1 is a +1, group 2 is a +2, group 3 is +3, and then we have our group 5, which will be a -3, group 6 a -2, and group 7 a -1. So let's talk about sulfur now. Sulfur itself, remember, I want you to think about what group number it's in. Then from there, I want you to know how many valence electrons it has. Remember, the group number equals the number of valence electrons. From there, what does it need to acquire an octet? It has to acquire that complete octet. Sulfur is a non-metal, so it's going to gain. And then what is the overall charge that it's going to gain? And remember, this will be negative because it's an anion, because it is a non-metal. So take a moment and do it. And then as you go through, hopefully you got that sulfur is in group 6. That means it has 6 valence electrons. It will have to gain 2. And its charge is going to be 6 minus 8, which will give us a negative 2 for a charge. So let's think about actually forming ionic bonds now. When we form an ionic bond, our metal is going to give up its electron and the nonmetal is going to take it or gain it. And we form 2 charges, 2 actual ions that then are bonded next to each other. So an ionic compound, you need to know, consists of a positive and a negative ions. They are attracted for the forces between them because opposites attract, so a positive and a negative will attract each other, and they form what we call an ionic bond. All of ionic compounds have very high melting points and high boiling points, and they are solid at room temperature. Take the best example is table salt, so sodium chloride. You probably have it in your kitchen now. It is completely solid at room temperature. Have you ever tried to melt salt? If you ever hold it under an open flame, not that I suggest you doing this, but it will not melt and it will not burn, okay? It takes a very, very high BTU to have salt melt. And it also has a very high boiling point as well. So salt is that ionic compound. When we name all ionic compounds, we're going to name them in a certain fashion. We always name the metal first, and then the non-metal comes second. So in our chemical formula, when we're seeing it as elements represented by their symbols, the first element symbol you will see will be the metal, and then the second one should be the non-metal. And we always represent these in the lowest whole number ratio of ions, okay? So if they have a, say I wanted to do magnesium sulfide. So I have magnesium, which is in group 2, and sulfur, which is in group 6. Magnesium has a +2 charge, sulfur has a -2 charge. Now, if we add them together, +2 -2 is neutral, and we want our whole overall compound to be neutral because all compounds are neutral and always have a 0 charge. They're charge balanced. So instead of being Mg2S2, it's actually just Mgs, okay? They're one of each. Now in the formula, we have to remember we are a sum, so our actual compound is the sum of all the positive and negative charges, and it always has to sum up to 0. So the charges are always balanced. So if we're looking at sodium chloride, sodium is going to lose its valence electron, chlorine is going to gain it, okay? And we're going to write the symbol of the metal first, so we'll write Na first, and then we'll write the symbol of chlorine, the nonmetal, Cl. So to be NaCl. If we are drawing magnesium chloride, in this case, magnesium is going to lose 2 valence electrons. And because of that, because we have to charge balance, chloride means we're going to need 2 chlorine atoms, okay? Because they're both a -1 to take on that +2 charge. So we'll need 2 of them. So technically, magnesium chloride will actually have the formula MgCl2. And again, I want you to watch the little videos that I'm going to post on how to draw these and how to name them, and we'll go over some more of these formulas because I have some tips and tricks that I can show you. So there we are, there's our magnesium chloride. And if we're looking at charge balancing in sodium sulfide, So for sodium sulfide, in this case, I have 2 metals and 1 nonmetal. Now sodium, again, they're each going to lose 1 valence electron. Sulfur is in group 2, so it has a -2 charge. It's going to take each one on. So it'd be Na₂S. So anytime you hear like sodium sulfide or magnesium chloride, even though they have multiple atoms in there, but there's not a multiple in the name, it's not like disodium sulfide, that denotes an ionic bond. That's the one key thing to naming ionic bonds. We don't tell you in the name how many of the atoms there are. We just expect you to be able to do it based on the charge balance itself and knowing that they balance themselves in charges. So I want you to take the time and write the correct formula that you can make with the following ionic compounds. So I want you to make a compound out of sodium and sulfur. Okay, we just did this one, but that's okay. So sodium is a +1 charge, sulfur is a -2 charge. That means that we'll need 2 sodium atoms for every sulfur atom. So it'll be Na₂S. If we're looking at aluminum chloride, Al3, okay, or Al3+ and Cl-. In this case, aluminum has a +3 charge. This has a -1. This means I need to have 3 chlorines for every one of the aluminums. So right there, our formula will be AlCl3. So there'd be 3 of these. Now our next one is magnesium nitride. So we have magnesium with a +2 charge and nitrogen with a -3 charge. This one's a little hard. We have to think of the least common denominator, excuse me. So in this case, what is our lowest common denominator between 2 and 3? That would be 6. So I need to have a +6 charge and a -6 charge to be able to charge balance. So what do I have to multiply this 2 by to get 6? That would be 3. So I'd have Mg3, and then we're going to have nitrogen here. It has a 3 here, so we need to multiply it by 2. So it will be Mg3N2. And I'll go over some tips and tricks that we can do later on, so check those videos, okay, if you're a little confused. Now when we name and write these ionic formulas, the metal is always written first, and then we name our non-metal ion, but we write it with the first syllable and then follow it by "ide." So chlorine becomes chloride, okay? Bromine becomes bromide. Fluorine becomes fluoride. Oxygen becomes oxide. Nitrogen becomes nitride. Sulfur becomes sulfide. Phosphorus becomes phosphide. Those are just trying to give you some ideas, okay? We always put a space in between the metal and the non-metal as well. So Ki is made up of potassium and iodide. So it becomes, or iodine, excuse me, but it becomes potassium iodide. MgBr2 is magnesium bromide. Al2O3 is aluminum oxide. So our guide to naming our ionic compounds, we have to kind of think of first, what is the cation, what is the anion? Then we're going to name the cation or the metal first by its element's name. Then we name the anion or the nonmetal by its first syllable of its element name, followed by "ide." Okay? So this is just an example. I would like you to name Mg3N2. Now here's the big thing. It doesn't really matter what these numbers are down here. These numbers just denote how many magnesiums and how many nitrogens are needed. What you need to know is that the cation always comes first. That's the metal. So that would be magnesium. We'd write it with its whole name. Now, N stands for nitrogen. That is our nonmetal, so that comes second. But we're going to take the first syllable and then follow it by "ide." So it becomes nitride. So magnesium nitride would be the name. So let's name these following compounds. CaO. Ca is calcium, O is oxygen. So this becomes calcium oxide. KBr. K is potassium, Br is bromine. So this becomes potassium bromide. Al2O3 becomes aluminum oxide. MgCl2, magnesium chloride. So there are those names. I just want you to feel comfortable doing it. Remember, there's a space in between. We're going to discuss slightly polyatomic ions. I'm not going to do too much on this. You will maybe see one or two on an exam and that's it. So it's not a huge lot or a big component. So don't get frustrated over this. And I will put up separate videos on how to solve these. But a polyatomic ion is a group of atoms that has an overall charge. These are always groups of nonmetals. Okay, so polyatomic ions are usually anions. And our examples, there's only one that's positive. I'll give you that one. Still made up, ironically, of nonmetals, but it is ammonium. So that's an H4+. Other than that, we have nitrate, carbonate, hydrogen carbonate, or bicarbonate is a big thing. Hydroxide, nitride, and phosphate. The ones that we will see common in biochemistry are bicarbonate. That's a big one, and carbonate. But bicarbonate is what's actually going to play a big role when we start talking actually about your blood and blood pH, okay? And then phosphate. This is a big part of ATP. When we talk about these namings of these anions and the polyatomic ions, most of them end in ate, ATE, like nitrate or phosphate, depending on the number of oxygens they have. Now, when we take one less oxygen, so we remove one more from the group, we end up in an ite. And doesn't really matter, but that's how we get to the difference between a nitrate and a nitrite, and a phosphate and a phosphite. And this really doesn't deal with you too much. It deals with general chemistry, but just know that these names are different and do mean things. Okay. Here are just some names of them that you'll commonly see and their charges associated with them. The big thing is polyatomic ions are always seen, when they're in a formula, are always seen in parentheses, and we treat them as a whole group altogether. So when we talk about compounds that are containing polyatomic ions, the big thing is these polyatomic ions must be associated with an ion of the opposite charge. So if I have a nitrate ion, like NO3-, I'm going to have some form of a positive ion next to it, okay? They have to be associated together. They're always in ionic compounds. So polyatomic ions form ionic bonds. So in this case, I have a calcium with a +2 charge, nitrate has a -1 charge. I'm treating this as a whole, all together, like it's its own element. So I'm never going to change this number here, that 3. I'm only going to look at how many do I need to change overall. That would come above here, like I need 2 of these or 1 of these. In this case, because I have a +2 and a -1, I'm only going to need 1 calcium ion, and for every 1 calcium ion, I'm going to need 2 nitrate ions to get that complete charge balance. Okay, +2, and I want a -2 over here. And if I were to write out its name, calcium nitrate, it's going to look at Ca, and then I'm going to put in parentheses the polyatomic ion, that NO3, put the parentheses in, and then I put the number of them I need, the 2. Okay. So when we write these, you have to identify the cation and then the polyatomic anion. We're going to balance those charges, and then we write them with a cation first and then the anion. So if I'm looking at aluminum hydroxide, and these are common bases that we'll talk about are the hydroxides, the really important strong bases. In this case, I have a +3 charge and a -1. I am going to need 3 of those -1 charges to balance with that +3. So when I write my formula, it's going to look as an Al parentheses OH. We'll put that parentheses back in, 3 as the subscript, okay? That's the number of those OHs I need. When we name them, it's the same idea with naming. We just name the cation first, and then you name the polyatomic anion. Simple as that. So if I wanted you to name K2SO4, okay? So the cation is K2, or K positive, that's a potassium. And then our SO4 here is a sulfate ion. So this becomes potassium sulfate. And these are just giving you some examples of where you see these. Barium sulfate is the medium used for when we talk about like a barium swallow or a contrast for x-rays. Calcium carbonate is an antacid. Calcium phosphate is a dietary supplement. You have calcium sulfite, which is used to preserve fruit juices and sometimes ciders. You also have calcium sulfate, so just one more oxygen than the sulfite. And in this case, that is what's used in plaster casts. Silver nitrate is a topical anti-infective. Silver nitrate is actually used to cauterize. So sometimes you'll see silver nitrate sticks if you are on like the med surg floor, and they might use it to cauterize wounds. You also have sodium bicarbonate, which is an antacid. Zinc phosphate is used in dentistry as cement. Iron phosphate is a food additive. If you're looking at potassium carbonate, that's Alka-Seltzer. Also found in diuretics as well. Aluminum sulfate is an anti-infective or an antiperspirant. It's one that's commonly seen in deodorant antiperspirants. Aluminum phosphate is that antacid again. And then magnesium sulfate is used as Epsom salt. So just some general interesting things for you and where they're coming in.